Let's start our session. So, hello everybody. Today we have a pleasure to have Larus Thorlacius talk. He will tell us about page curve for an evaporating black hole in asymptotically flat space-time. Oh, 45 minutes, please.
Thank you. So yes, I'd like to start by thanking the organizers for the opportunity to present this work. So what I'm going to talk about is a recent paper that I wrote with my colleagues here in Iceland, Friðrik Gautason, Lukas Schneiderbauer, and Vatse Sebertma. And then it's appeared here on the archive. And so what we are doing in this paper is extending some very interesting recent observations about how one can use semi-classical methods to obtain the page curve for black holes. Now this work that we are extending was for ADS black holes, where the black holes were arranged to evaporate by coupling them to an external path. And what we wanted to see is if this could be extended to a situation where the black hole was actually an asymptotically flat spacetime. And we find that we can do this, and at least in the simplified context of certain two-dimensional models that were studied back in the 90s. So what I want to do in the talk is maybe first spend some time reminding people and reviewing these models, since these are maybe not things that people have been working on, at least not everyone. And so I'll run through sort of the definitions, show how one can find explicit black hole solutions, both eternal static black holes that are two-sided, and also dynamical solutions one can find analytically for general incoming matter configurations. And then in these models, there's a very nice way to characterize the Hawking effect, and sort of through the conformal anomaly. So I'll describe that briefly, and then come back to the problem at hand, which is to use or to adapt to these models these computations that have been carried out recently about the generalized entropy, and extremizing that and finding finding the results that reflect what you expect from a unitary evolution. And maybe the surprising part here is that you're in fact able to get a result that you expect from unitarity from a semi-classical calculation, because in these models it's very clear that they are not sufficient to, in fact, if one looks at black hole evolution in these models, it's pretty clear that if all you do is a semi-classical computation, you will see information loss. So, and yet somehow the semi-classical geometry has some knowledge about the underlying unitary evolution. Now, this approach, this recent work was described very nicely in talks on Monday by Juan and Neta, so I will not be going into too much detail there. But they both emphasized that this result is surprising, and that the semi-classical theory is surprisingly effective. And what we're going to be finding is that perhaps it's even more surprisingly effective, that we can really also extend this to a setting where we have the black hole that's not in ADS spacetime. And yet we can use this holographic prescription if we adapt it in a certain way, and it gives us a result that seems to be precisely what one would expect. And so what the page curve describes is, it describes the entanglement entropy between, or the entanglement entropy of the subsystem that consists of the outgoing Hawking radiation from a black hole. So one imagines that to form a black hole from an initially pure state, some infalling matter, this black hole then evaporates due to the Hawking effect, and the outgoing Hawking radiation. If we view that as a subset of the full quantum system, one can imagine calculating, and in fact we'll have a prescription for calculating its entanglement entropy with the rest, which is then the remainder of the black hole. And then the expectation is that early on, this will be an increasing function of time, and by time, I mean here time as measured by asymptotic observers, and that it'll grow, but it cannot grow indefinitely because eventually this Hawking radiation is carrying almost all the degrees of freedom of the system, and so there's very few degrees of freedom left in the black hole to be entangled with, and therefore this entanglement entropy should turn over and eventually go back to zero. And this is shown based on general arguments by assuming unitary evolution by Page back in the early 90s. And what's interesting in these very recent, more recent work is that one can actually see this behavior with a prescription, and it's important to keep in mind that it's still a prescription that we're applying here, but that prescription gives a result that really reflects this. And basically, it is usually referred to as the quantum Ryutake-Yanagi prescription for computing the generalized entropy system. And it has two terms. It has an area term and a bulk piece. And if you ignore this area term and only compute the bulk piece, you get this rising curve over here, which amounts to what you would see if you just used Hawking's computation of the so having a purely thermal outgoing radiation. But then after a while, one finds that this, and I'll discuss these terms a little bit more later on, and they were discussed in quite generally on Monday. After a certain time, this area term will take over, dominate the result, and it will in fact, in these black holes that we are working with, we will in fact explicitly see that how this area term is then shrinking and gives us this, this expression here, or this curve. And so the basic question that we ask in this work is whether we can adapt this prescription to an asymptotically flat spacetime. And of course, a priori, that's not obvious that you should be able to do that because this is a holographic prescription. And the key to this is that the asymptotically flat spacetime that we're working in has asymptotically a linear, a running dilaton in the background. And this will be the key to why this works, I believe. Okay, so let me give you an outline of how we're going to go about this. So what we'll first, after an introduction where I will work out or show you what these black holes look like, what one finds is that these 2D black holes, they have causal structure or Penrose diagrams that are identical to what you expect for a Schwarzschild black hole in 4 dimensions, so that's nice. And so what I'm showing here is the Penrose diagram of black hole that's formed by some infalling. Basically, this is what we have in mind here for simplicity is to think about a concentrated shock wave of incoming energy here that forms a black hole. That black hole will then evaporate and gradually, so it'll send out Hawking radiation, and then eventually it will have lost all its mass and we get back to the vacuum. And in this model, sort of modulo there's a little bit of patching that needs to be done here at the end point, but we can sort of put that down to an uncertainty about physics at the Planck scale anyway. But once we have that, then we have a late time geometry where the black hole is gone and there's just all this Hawking radiation that's going on. So that's precisely what one wants to have to address this kind of issue. So that's the model that we're going to be working with. We're going to adapt this formula to this model and evaluate the terms. And in order to do that, we're going to follow a very nice idea that was explained in this paper by Almeri and collaborators last summer, which is to assume that the matter that forms the black hole is actually described by some strongly coupled conformal field theory, and so that we can use an ADS3 CFT2 holography to actually calculate this term, this second term here. Okay. And then what we'll find is that a story that's very similar to what was in the ADS. What's maybe very appealing about this particular setup is that the way we divide the system into the outgoing Hawking radiation and the rest is by defining a curve. It's at some fixed location far away from the black hole. It's important that this curve is somewhere really deep into the asymptotically linear dilaton regime. And then the entanglement entropy that we're computing as a function of time for an observer who's sitting on this curve, we're computing the entanglement entropy between the radiation that's already passed out to the outside region and whatever is on the inside, which is whatever radiation is on its way out to the anchor curve and the remaining black hole. And a further nice feature of these models is that we're able to do all of this explicitly. We have, in fact, analytic solutions for the semi-classical black holes, evaporating black hole, and then at least to leading order in an approximation where the initial mass of the black hole is large compared to the central charge of the matter theory in appropriate units, and that in turn is large compared to a number of order 1, in order to both motivate using the holography to calculate the Spock term here, but also we need that so to simplify the semi-classical analysis of the model. If we have a large central charge in the matter sector, we can ignore, at the order we're working, we can ignore loop corrections that involve the metric and the dilaton in the 2D gravity theory. And then what we find is the same curve that I showed on the previous slide, but this time, this is not just a sketch. This is actually a result of, it's an explicit result of a computation in this model. So let me start with an introduction of the model. Now, maybe I should ask, are there any questions at this point before I continue? If not, then I will just keep going. And so the model that we work with was introduced by Callan, Giddings, Harvey, and Strominger in the early 90s. It's a model that descends from dilaton gravity in 4 dimensions. It's in fact an effective description for the radial modes that are moving in the background of a near extremal magnetically charged black hole in a certain 4-dimensional dilaton theory. None of that is very important for us here. Except that this model actually is very closely related to some backgrounds in string theory that are known to have a holographic description. It's closely related to some NS and S5 brains where one can do holography in an asymptotically linear dilaton setting, so that at least we can use that, even though we're not going to use that explicitly here, we can use that to motivate using this holographic prescription that we're going to apply here. Okay, now in the original CGHS model, the fields were a 2-dimensional metric, a dilaton field, which is in fact related to the area of a transverse 2-sphere in the dilaton, in the 4-dimensional theory. And that'll be important for us to keep track of that. There's a length scale that's set by also that it inherits from the 4-dimensional theory. We're going to set that, work with units where that length scale is 1 throughout. And then in order to have interesting dynamics, Callan et al., they coupled a set of free scalars to the theory. The free scalars, you took a large number of them for the reasons that I mentioned earlier. in order to be able to be sure that the matter one-loop corrections would dominate over the dilaton gravity sector. And so this is the model, and we're going to have, so we work in conformal gauge throughout this talk. And in conformal gauge, this model has rather simple equations which can be solved, as I said explicitly. Now there's a further convenient gauge choice. Basically, this last equation here allows us to do a conformal reparameterization to set rho equal to pi. So the conformal factor of the 2D metric can be identified with the dilaton field. And this simplifies the equations and also gives you directly, when you plot solutions in this coordinate system, you find that these are in fact the analog of Kruskal coordinates, so one can see the global geometry rather easily here. Okay. Now, but as one can quickly easily see here, that if you couple a different matter sector, still a conformal theory, but not free fields, the gravitational response is going to be the same. So those, so the black holes that we're interested in, they don't rely on these being free fields. And this is going to be important later on because we're going to assume that we actually have strongly coupled matter and use holography to be part of the computation. Okay, so the solutions are well known to these models. I'll just very briefly run through them. There is the vacuum solution, which is given, looks like this in Kruskal coordinates. It's not linear in these coordinates, but if you take logarithm of the coordinates, you'll get a set of coordinates where it is. These are basically given down here. So in the linear dilaton vacuum, you will find that the dilaton is in fact linear in this sigma coordinate here. So these are the coordinates that would be used by observers, distant observers, and in particular on these anchor curves that we're going to introduce. There's a one-parameter family of that generalizes the linear dilaton vacuum, which is the static black hole solutions. And it's convenient to actually rescale the mass out of these formulas, and then we get an expression here which looks very much, it's the Lorentzian version of the usual 2D cigar geometry. And then the mass is still here in the dilaton in this. And the Penrose diagram of this metric here, so we have at V or U equal to 0, we have a horizon, and at the product V equals VU is equal to 1, we have a singularity. And this looks very much like Schwarzschild black hole in 4 dimensions, but there are important differences. In particular, when we do thermodynamics on these vacuums, we'll find that this M parameter here is proportional to the mass. That's not surprising, of course. We can easily find a Hawking temperature, and the Hawking temperature turns out to be, and I reintroduced the lambda here, which I will otherwise put to 1. The Hawking temperature, we note, is the same for all of these black holes. It's an intriguing feature, which certainly makes them different from. It means that they don't have a negative specific heat, but they have an infinite specific heat, which is a little bit unphysical. The entropy, the Bekenstein-Hawking entropy, is given by the value of the dilaton at the horizon. And this also, when you go through the dimensional reduction, you will see that this is in fact an area. This is the area, this is 1/4 of the area of the black hole, the higher dimensional black hole in Planck units. And so that's another thing that we'll keep in mind as we go along. Okay, so these are the eternal black holes. A simple matter to add matter, then you will have, you'll get some dynamical response from the geometry that can also be solved for in closed form. So for an arbitrary matter distribution coming in here from the right, we can find the exact solution. And as I mentioned earlier, we are interested for the most part in the behavior of the geometry on the one hand before the matter starts to come in, and then on the other, well after it's settled down into a black hole and is evaporating. And for that, we may as well take this to be a concentrated incoming flux and just view shock waves. So if you have a shock wave that comes in these rescaled coordinates at V equal to 1, The geometry is very simple. It's the linear dilaton vacuum here before the shock wave comes in. And then we have this solution up here, which describes the black hole. So this is the classical. There are various coordinates one wants to keep track of. These are the Kruskal coordinates that we are, for the most part, going to be using. But when we want to talk about times, for example, for asymptotic observers, we would go to these sigma coordinates here, and the asymptotic time is given. But that can easily be read off then from whatever other. These are very explicit coordinate transformations one can do here. And another important coordinate system is, in fact, the coordinates in which this linear dilaton vacuum is actually, one can see that it's a flat geometry manifestly. And those are related to the Kruskal coordinates like this. All right, so these are the players at the classical level. Let me very briefly run through this rather nice description of the Hawking effect that is dates back to this paper by CGHNS, and actually it predates that work by Christensen and Fulling back in the 70s. The observation is simply that in a curved background, like these black hole backgrounds, the matter stress tensor will have a trace that in our conformal gauge, it can be written like this. And then one can take the conservation equations for energy conservation in these two-dimensional models, and one can simply integrate those equations to give us the remaining non-vanishing components, the other components of the stress tensor. They're given by this formula here. But because we are integrating here, there will be these integration functions here that one needs to keep track of. It will be important later on. And one can see that these integration functions of integration, they actually transform in a characteristic, in a sort of well-known way. So if we do a conformal reparameterization of the coordinates, so we let the light cone coordinates be a function of each, so y plus of x plus and y minus of x minus, the conformal factor will transform in a simple fashion. And this, a simple calculation will tell you that the stress tensor will in fact pick up an anomalous piece here. And this is the conformal anomaly here where this curly brackets here is the Schwarzschild derivative. And if you go back and look at this, if you want this formula to hold in any conformal coordinate system, then you'll better also transform your keys like this. And this was used by Callan and company to establish a Hawking effect in these simple geometries. If you simply made the physical condition that there should be no outgoing radiation here before there's any matter that has come in. And you work in the coordinate system where the metric is manifestly flat down here. That means these terms are vanishing. And that means their T minus in that coordinate system has to be vanishing as well. But then when you transform to the coordinates that you use for an asymptotic observer, this Schwarzschild derivative in fact leads to an outgoing flux, which is given here. And if you stare at this for a little bit, you'll see that it starts out being vanishing, and then it turns on and then goes to a constant value. And of course, we haven't taken any back reaction into account here, so it'll just keep radiating forever here. And it doesn't change with time because the temperature is not changing with time. It wasn't a function of the black hole mass. Okay. Now, one can also, in a rather simple way, get the leading order back reaction into play here. And so CGHNS, what they did was to add this Polyakov term to the action. It's a non-local in general term. This comes from just integrating out the matter fields at one look. And but it looks more manageable in the conformal gauge. And then you can actually see, if you add this to the action and you rederive your equations of motion, you'll find that you'll see that the black hole is actually now responding to so you get some back reaction into account. And what we did shortly afterwards was to realize that if you added another term, which is allowed by general covariance, and sort of comes in at the same order as this one, and in particular doesn't disturb the classical limit. And then these semi-classical equations are just as solvable as the classical ones were. And you can really write things down in rather compact form. And the way you do that is you introduce you do a field redefinition to this variable we call omega here, and then you'll find that the equations of motion here look almost the same as they did before. And further bonus is that this vacuum, the flat vacuum, actually is also can be written very explicitly here. But there is a subtlety though here, and that is that this field redefinition that I've written down here, it's not one-to-one. And so there is in fact a boundary in the omega field space, and generically you would find curvature singularity if you go to this value here. It turns out that you can implement some boundary conditions that avoid curvature singularity, at least where these things are, where this curve is finite. Sorry, it's time-like. And then when it's space-like, it is in fact the black hole singularity that you will find. It occurs at this value of the dilaton. Okay. So that's the basic story that we have here. So one can look again for black hole solutions. The eternal black hole solution is very, very simple here. It's pretty much identical to what we had at the classical level. But when you look at it more closely, you'll find that this is in fact a black hole that's in equilibrium with the thermal bath. So there's an equilibrium of inflow from infinity and then the Hawking radiation that goes out. And you can deal with that in this model without running into problems with the Jeans instability, and that's because of the dilaton is running, and so the gravitational coupling is actually becoming so weak far away that even though you have an infinite amount of radiation, the back reaction is not catastrophic. Okay, now more interestingly, you can still form, you can still find explicit solutions to the dynamical black holes. So it's a shock wave. They're a little bit more complicated. There are now these log pieces that come in, and those are very important because those are precisely the ones that let the black hole shrink as the evaporation proceeds. And so these are the beasts that we're going to be working with. So I will focus primarily on the dynamical situation because that's a black hole that forms and then goes away, but we can also do the same or similar computations. I'll show you the results at the end for the eternal black hole. And the computation is actually simpler in the eternal case. And so the assumption is going to go into the computation now is that we form a black hole that has a large mass. So this is why, so that we can trust these leading order semi-classical formulas that we have. And so there's a small parameter here, epsilon, which is basically C over, turns out C over 48m is a parameter that often comes up. For instance, the lifetime of the black hole is going to be precisely 1 over epsilon in this solution here. And so this is the Kruskal diagram for this black hole. Here comes in the shock wave. There's a linear dilaton here. There's a black hole. Part of the geometry is up here. And here's the Penrose diagram that I showed earlier. Okay. So these are the black holes that we have. And again, maybe I'll ask, are there questions or something unclear about those before I move on to the generalized entropy? Okay, so then what the plan is then, having these black hole solutions in hand, we want to see if we can adapt this prescription to this 1 + 1 dimensional setting. And the way we're going to do that is we're going to, instead of having an ADS boundary where we couple the system to some external bath, here we're going to simply look at, we're going to place at an arbitrary position, but far away from the black hole, a curve. Convenient is, for example, to pick a constant value of the dilaton, that it gives you a coordinate invariant notion of a fixed position. And that is what we'll divide our system into. So there's the outside, which carries the outgoing Hawking radiation, and then the inside that has the remaining black hole. Now, these, in the higher dimensional setting, A here is would be a surface on the boundary, some subset of the boundary. And for the particular computation that we do, you would actually take A to be the entire ADS boundary. And for us, that's going to be at a given time here, is simply going to be a point on this anchor curve, because we are automatically here, we have a transverse two-sphere, if you like, from the higher dimensional point of view is included. We're going to work with this, and then I is a surface that's inside. When you're doing this in ADS, it's a surface inside ADS that's homologous to the boundary surface A, and whose area you compute when you're applying the usual Ryutaki-Yanagi prescription. So for us, that's simply going to be some point in here, and it turns out it's going to be a point that's when we do an extremization later on, we're going to find it's a point that's just inside the event horizon of the black hole, and this will find an extremum is there at least, as soon as you wait it one scrambling time after you form the black hole, you'll find that there is a point where you'll have an interesting result for. So, and then as time evolves along the boundary curve, this island will migrate towards actually the singularity and the horizon, sort of merges into that. But at that point, of course, we cannot trust these semi-classical computations anymore. And then the surface whose von Neumann entropy of the matter we're going to compute on is basically, in this case, it's going to be a space-like curve that connects these endpoints, one on the anchor curve and then the island. And then what we will do is we'll fix the anchor point, and then we'll ask what location of an island here is going to give us an extremum for this expression here. But first, of course, we have to then decide how we're going to calculate that. The area term, let's look at that first. As I said earlier, we have a notion of area here that we inherit from higher dimensions. That's basically given that the area of the transverse two-sphere, when you do the numbers in Planck units, is going to be 8 times e to the minus the dilaton. And then in a semi-classical theory, it's very natural to replace the e to the minus 2 phi with the omega function here, which at leading order, when you have a large black hole, they're going to be the same. And so our prescription is then we're going to compute the area term, and simply we're going to evaluate this omega here at the location of the island, and we're going to subtract off this critical area. Now, for an island out here, that's not going to be matter. This is just so that in the absence of an island, we'll place the point on this boundary curve here, which is playing the role of the origin of the coordinates, and then you want the area to be 0, so adjust it there. Okay, now for the bulk term, we are going to follow these authors here, and we're going to assume that we have a strongly coupled 2D matter theory that has its own holographic description in 3 dimensions. So that's a different holography than the one that's implied by using this area formula here. And then we'll find that if we can embed this as a boundary theory into an ADS, an asymptotically ADS3 space, and in fact, if we play our cards right, we can make it a pure ADS3. Well, all we have to do is to calculate the length of a geodesic that connects these points A and I. And so that's what we'll do. And the 3D length scale is related to the 2D central charge as by the Brown-Heno formula. Okay, so that's then how we're going to proceed, but we need to do this embedding into ADS in a couple of steps. And the first step that we're instructed to do by these authors here is to look for a particular set of light cone coordinates where these t plus and minus functions are equal to 0. And then you do a while rescaling to strip off this conformal factor. And at that point, you're in a flat metric, and you picked a coordinate system where this guy's vanish. And then if we go back to the definition of, or what our result for the stress tensor, if the rho is 0 and the t is 0, then these guys are 0, and therefore you will have found basically a setup where your matter CFT is in a vacuum state. And then you can, at least close to the boundary, we can ensure that, and with these sort of the parameters that I have assumed, I've assumed that I have a large C and then an even larger M. I will be able to do the computation in pure ADS now. And furthermore, this Weil transformation that I have to do, I can actually, once I'm in 3 dimensions, I can view it basically as a conformal transformation, sorry, a coordinate transformation on Z, involving Z. And that tells me that before doing the Weil transformation, if I had a boundary, so to do my holographic computation, I need a regulator. But now, once I do the Weil transformation, I'll find that this boundary is mapped into a surface or a curve in ADS3. Yeah, that's going to be an important piece in our computation, because now we need to calculate the length of a geodesic in ADS3. Of course, if it goes all the way to the boundary, it's going to be infinite. But we are now instructed to stop our computation at this location here. So what I've dropped an overall delta dependent constant here, which is the same for all my geodesics, but there is an important dynamical information that comes from the 2D theory through here. And then basically a standard computation in ADS3 gives us this expression here for the bulk contribution. And now we want to calculate that for these black holes that we. Okay, so let's do that for the evaporating black hole. First of all, so we're going to look at the solution that I talked about earlier, which has the linear dilaton vacuum, and then we send a shock wave in. Then it's clear that this T minus here, as I discussed when we were talking about the Hawking effect earlier, that one is 0 if we pick the omega coordinates, the flat coordinates in the initial dilaton vacuum. So that's good. On the other hand, in those coordinates, the T plus includes all the energy of the incoming shock wave. So that's maybe not so good. But there's a way around that, which was basically we can use an observation from these authors here who were in fact calculating the entanglement entropy of radiation outside black holes in precisely these theories. And their observation was that if you in fact take the infalling matter to be in a coherent state, so the quantum state of the infalling matter is a coherent state that's built on this vacuum that is be used by observers, inertial observers in the linear dilaton vacuum, then in fact the entanglement entropy, the von Neumann entropy, is actually independent of the excitation than if it's a coherent state. And using a coherent state seems reasonable. We want to make a classical black hole, so you want to have what looks as much like a classical quantum configuration as you can. Their point was that if you don't do this, you could actually cook up some arcane matter states that would violate the generalized second law, etc. So this seems like a reasonable assumption to adopt, that we have a coherent state. And then for us, it's also very useful because it allows us now to simply do the computation in these omega plus omega minus coordinates. And we'll get the same answer as for the coherent state as we would if we had just used the vacuum. So this is what we'll do. Now, so we're going to do 2 computations. We're going to do this with an island included, and also for comparison, we're going to do a computation which does not have an island. So then this surface that we're going to calculate this on has to extend all the way to the interior point here. And I think as I'm not going to go into the details of it. It's a straightforward computation. You write down this generalized entropy. It has an area term in the island case. which we can just read off from the semi-classical solution for the black hole. It also has, when you plug in to the expression that we had for the bulk piece, you get something that looks like this. You can now, and the rule of procedure is you fix a point on the anchor curve, so those are the VA and the UA, and then you extremize this over the location of your island, or the inside point that you're going to cut off this surface at, and you get these equations here, which are a little bit, it takes a little bit of massaging, but in this limit that I mentioned earlier, that if m is much larger than c and c is in turn much larger than 1, you find a very simple result. You find that this is in fact at all times dominated by the area term here, and you find that well, you do get actually a contribution from the other term that sort of adjusts this to give you exactly what you want, which is the retarded time out here. So this actually takes into account the part of that it takes time for the radiation to actually get out to the anchor. Okay. I'm not going to go into the details of this, but this it's a straightforward computation. Now, for the no island configuration, we're going to place the anchor point in here. Now, you might worry about that because this is actually, if you look at the equations of the RST model, this is a location where your coupling is no longer small. It's in fact a strong coupling, pointed strong coupling. But on the other hand, if you think back to the interpretation of this as an origin of coordinates, you don't really expect anything dramatic to happen there. And in fact, what we find is when we do the computation, and we find that the leading order behavior that I'll show you here at the bottom actually doesn't even, you have to go to subleading order to see even that any dependence on where exactly you place this point here. So this is a very robust result for the no island configuration. You see that, as expected, it basically is a growing function of time on the, and you can do more things. You can actually figure out, for example, the location of the island. I didn't prepare any slide on that, but you can ask, for example, if you send a message earlier, you can ask, at what time do I have to send a message from this anchor curve that would be received, a null message that would be received in here? It turns out that has to be sent of order a scrambling time, which is log m in this model, before the anchor point of the time of the anchor point that you're considering. And this is entirely analogous to a result that was obtained in the ADS story earlier. Now, if you compare these two, you'll see that this guy is a growing function, the other one is linearly going down. So as promised, we're going to get here these two curves, and this is now, this order these are exact results. One finds that the black hole actually, you'll notice that the rate of growth here, the slope is twice the slope here, and that is actually in line with general expectations. In fact, this was already argued for in this paper by Viola et al. Back in the 90s. The point is that the outgoing radiation is actually, so the emission process is in fact an irreversible process. So you expect the radiation gained, the entropy gained by the radiation going out should exceed the entropy lost by the black hole. And in fact, in these 2D models, you'll find that it is precisely a factor of 2. And that gives us a page time then that'll be exactly 1/3 of the lifetime of the black hole. So this is what we get for the, and we can, I guess, interpret this in a couple of different ways. We can say that, okay, this is telling us that sort of a posteriori, we can justify having used this asymptotically linear dilaton holography, if you like. It may also be telling us that this formula, this quantum real-time active formula, is simply has some applicability even outside holography. But in any case, it seems to be, it's giving us precisely what one would have expected here. And we can also do a computation for the eternal black hole. It's actually rather, it's simpler. I'm not going to go into the details here, but you'll find in that case, just like in ADS, that the islands that extremize the story here, they are sitting outside. They're sitting just outside the event horizon instead of just inside. And again, if you want to send a signal from the anchor curve to the island, you have to do it time of order of scrambling time for the time that you are interested in on the anchor curve. And in this case, you'll find that the island contribution, once these islands come into place, they actually give you a value that just remains constant, whereas the no islands answer is growing as a function of time. And so if you then are instructed to pick the extremum that gives you the minimal generalized entropy, you cross over here. This is, of course, looks more like the pictures that you get in the ADS, because the ADS black holes tend to, they're always in equilibrium with some outside system. They're not really vibrating, or they're not shrinking. And in this computation, it's kind of nice to see that the coordinate system in which you're instructed to do the one where the t's, t plus and t minus vanish, are precisely the Kruskal coordinates. And that's maybe not surprising, because those are the coordinates where in which you would define, with respect to which you would define positive frequency, for example, in the Unruh vacuum. So it's all hanging together rather nicely here. So it seems like we have an unreasonable effectiveness of semi-classical theory. Now, I did not go into in this talk, but we also have been studying these models in sort of a different context. We've been looking at holographic complexity in these models, and one also finds an unreasonable, almost, effectiveness of semi-classical theory there. That we're finding that the rate of growth of holographic complexity for an evaporating RST black hole very precisely tracks the number of degrees of freedom that you expect to be generating the complexity at the stretched horizon. So it seems like these semi-classical geometries really know a lot about more about quantum gravity maybe than one would naively have expected. So let me end it there.
Some questions, please, to ask. Questions, you just have to unmute yourself, okay?
So maybe I have a question. Maybe it's very naive, but is it possible to relate with the higher dimensional models and to generalize your approach for some higher dimensional models, like it was done in the works by Almieri, Marov, and Maxfield?
Obviously, that would be a very interesting thing to do. These models are very much tied into they're tied into two dimensions, because we're using the conformal anomaly to get our back reaction. And once we have the semi-classical, even though they have some higher dimensional pedigree, if you like, once we go through and we've focused on so our quantization only includes these radial modes at low energies, and once you do that, it's sort of lose the connection, the direct connection to the higher dimensional theories. Now, for the eternal black holes, I think this may be less of an issue, and I believe there is already out a paper that does do some computations for Schwarzschild black holes. And I haven't studied it in detail, but it seems that I think they claim to be getting answers that are very much in line with what you would expect. Now there, of course, for an eternal Schwarzschild black hole, you do have the issue of the Jeans instability, that you're really sort of assuming some thermal equilibrium in an ensemble that is not well posed. But it's obviously something that one would like to do, yes.
Thank you. And maybe one small question. And well, Is it, since you have a magnetic charge, maybe is it possible to relate your model with some superstring origin brains, like NS5 brain? And
yes, sure. Now this was done, I didn't write the reference, but this was done already back in the 90s by Strominger and Giddings, I believe.
Okay, thank you.
There is a direct sort of descent from some string construction. This is also why we are quite confident to use these holographic formulas in this case.
Thank you.
More questions, please. Okay.
I would like to ask a small question.
Mm-hmm.
Can you comment a little bit about the entanglement wedges in the asymptotically flat case, or is there any? Is it just something purely observer dependent, or is there any meaning for the entanglement wedge reconstruction in the asymptotically flat case of your model?
Well, again, I think it comes back to this, to the extent that you can do holography in these asymptotically linear dilaton backgrounds. So these are holographically dual to some non-conformal theories. I think it should, yeah, you should be able to. And another thing is, of course, that the island, if you like, is in these. It's a feature that's inside the black hole, or at least it doesn't extend beyond the horizon. It extends, you know, a very tiny amount. It's still within what you would call the stretched horizon, and so therefore, it's tempting to speculate that this should be a feature. You know, it should be something that you can work with for any black hole, and that it really, that there is a holography, if you like, at work between the horizon degrees of freedom and the black hole interior. This is certainly what these complexity computations that we've been doing is very strongly suggesting. And then those are all, and then you're no longer sort of reliant on having a holographic map in the region outside the black hole.
Thank you.
Okay. Please, more questions? Somebody come, just maybe to ask question. Okay, maybe I will ask also one technical questions. What do you expect about the position of page curve, the maximum of a page curve? For example, if we take into account the if we take into account not too much central charge calculations, so we take next correction, what we get. So we expect a maximum of page curve move on right, on the left. Can you just tell us, or this is unpredictable?
No, I think it is probably predictable to one leading order bit. And maybe actually by working a little harder with the model that we have, we should be able to pick up the sub-leading, the log behavior, which should tell you what the leading order. But for small values, of course, you know, I wouldn't want to bet, because, you know, but the leading behavior sort of as you do, if you like, a C over M expansion. There are log corrections that we dropped here, which are computable.
Mm-hmm.
But I mean, I could guess whether it goes left or right, but it would be just that I haven't done it. I haven't checked.
Okay, thank you very much. Please, more questions? If not, let's thank Larus again. Thank you very much for very interesting and stimulating talk. Thank you.